So let's look at solid liquid phase diagrams, and we'll just do two examples. The first is an example where we're going to have a liquid where A and B form an ideal solution in the liquid. And they form an ideal solution in the solid. And if we do this, and this is an example of something that does this, is a mixture of silver and gold. And if we do this, we get a phase diagram that's really, really simple. So we've got temperature, we've got mole fraction of B, and here we have the melting temperature of B. Here we have the melting temperature of A. And if we're cold, we have solid. If we're warm, we have liquid, or hot, I guess. And we have a two-phase coexistence region, liquid plus solid. And gold and silver are similar enough that they can substitute in each other's crystal lattices pretty interchangeably. So a silver atom and a gold atom, pretty interchangeable. And so they can form a solid solution or a liquid solution. So a solid solution just means that if you were to look at an electron micrograph of a silver-gold alloy, there's not clusters of silver or clusters of gold. They're just spread out evenly. The two types of atoms are spread out evenly. All right, this is actually pretty unusual because you have to have materials that have, since we're talking about solid here, that they can pack together and have the same type of IMFs, same type and strength. So this is actually, there's a few examples. This is the only one I could think of off the top of my head. Let's look at a different type of example, though. Let's look at something where we've got, and this is a really, really common scenario, where we have A and B form an ideal solution in the liquid. But they're totally insoluble in one another in the solid phase. Now if you do this, what happens is, let's go ahead and say we've got mole fraction of B. For our composition axis, we've got our temperature axis. We've got the melting temperature of pure A. We've got the melting temperature of pure B. What happens, well, if we look at this, we'll say, wait a minute, this looks just like our colligative property thing. We said, what happens if we have something that forms an ideal solution in liquid and isn't soluble in the solid phase? That is going to be a freezing point depression problem. So what's going to happen is the freezing point of B is going to be depressed as we add A into it. And the freezing point of A will be depressed as we add B into it. So both these curves go down, and at some point they meet. Oh, that didn't work out. This is supposed to be a horizontal line down here. So we have here is liquid, we have solid, we have liquid plus solid, we have liquid plus solid, but we need to identify what's going on down here. Well, down below this temperature here, we have only solid, but solid is going to be two different phases. So the phase that's rich in A we'll call the alpha phase, and that's just this very, very thin wedge here. It's so thin it might be represented as just a vertical line. And that is, since it's predominantly A, we'll call it alpha. So it's just traditional to name solid phases with Greek letters. So we'll have a very thin wedge here, which in your book could be just a vertical line. And it's a phase that is predominantly B, so we'll call it the beta phase. Okay? So this solid area down here, since it's two phases, we won't just call it solid, we'll call it alpha plus beta. There's two different solids, two different crystal structures. Okay? So if we were to take a slice of solid and cut it open and etch it with acid and look under a microscope, we'd actually see two different crystal structures. Okay, we'd see little crystals of beta phase and little crystals of alpha phase. Okay, all right. And up here, we really shouldn't call this liquid plus solid because it's specifically liquid plus beta phase. And this is liquid plus alpha phase. So this is a properly labeled liquid-solid phase diagram. And so you could actually graph these curves here and here just using the freezing point depression equation. Okay, so just to remind you what that equation was, to the extent that this is true, we know that if I wanted to graph this curve, I could just say that it's the temperature of that curve is Tm of component, oh heavens to Betsy, this is mislabeled. That should be B, and this should be A. I switched sides on myself. Okay, so it would be the melting temperature of component B minus, what do we have here? It would be, let's see, it would be RT for component B, the logarithm of the mole fraction of B all over the delta H of fusion of B. So this is not a new equation, right? This is the equation that we derived for freezing point depression when these two conditions are met. Ideal solubility in the liquid, no solubility in the solid. So notice the mole fraction of B is less than 1, so this is negative, so this whole term is negative, and so it depresses the freezing point. And we could write an equation just like that for this curve. So we've got two freezing point depression curves, and where they meet, we can't have liquid below that, and so we just have the two solid phases. Now this line here has a name. This is called the eutectic line. And eutectic is just from the Greek. It means easily melted. Okay. And let's go ahead and draw a fresh one of these. Oh, and this is the eutectic composition right through here. And the neat thing about eutectic is that if you take this and were to raise the temperature, it would have a nice sharp melting point as if it were a pure compound. And notice it's not only a sharp melting point, it's a very low one. It's the lowest you can get of any combination of these two materials, A and B. Let's go to the next picture here. I want to show you Gibbs phase rule with eutectic. So we've got alpha plus beta, alpha plus liquid, beta plus liquid, and just liquid. And notice that if we're here, we prepare a system at that temperature and composition, it's going to split into two phases, a liquid phase with that composition and a solid phase, beta, with that composition. So beta in this diagram is essentially pure B. And you could use the lever rule to look at that segment and see which is bigger to find out which. It looks like about 50-50. Okay, so how many degrees of freedom? Let's go ahead and work that problem. F is equal to, we got two components, you've got two phases, so that comes up to 2. But because pressure is fixed, we lose one of the degrees of freedom and we have 1 degree of freedom, which basically says if you gave me this composition, the temperature is fixed, right? It's that. Or if you gave me this composition, the temperature must be that, right? So we only have one, can only choose one variable. What about if you're down here though? What do you have on this line? We can see you have liquid, but you also have alpha, or beta and alpha. So all three are present. On the eutectic line, we can say that if we write components, whoa. Let's try again. If we can say components minus phases plus 2, that's going to be 2 components. We've got 3 phases present. So that's going to be 1. But remember, the pressure is fixed, so we've lost a variable. So F prime is equal to 1 less than that. It's equal to 0. What does that mean? That means you don't get to choose the temperature or the pressure. If you have all three phases present, and what are those three phases? They are alpha, beta, and liquid. If all three of those are present, then it must be that you're at this temperature, the eutectic temperature. And it must be the composition of the liquid is this, right? So, I don't know, it looks like about 75% compound, 75% B. Must be the composition of beta is this, which looks like about 100% B, and the composition of alpha is this, looks like about 100% A. So the compositions are not variant, and the temperature is not variant. It's an invariant. It's kind of like a triple point. We don't get to choose anything. Nature chooses for us. Okay? So those are two really common solid-liquid phase diagrams that you'll see.